So, first of all, I'd like to thank Mikhail for the invitation to speak here today and the invitation to talk about current and future research at the Image Permanence Institute. My name is Emma Richardson, and I'm the Director of Research at IPI. And we're a non-profit research organisation based at the Rochester Institute of Technology in New York State. And our name indicates really our initial purpose when the Institute was established back in 1985. But our research mission over the years has expanded into a number of different areas. There we go. Great. So when I first arrived at IPI in 2021, it was the first time the institution had a dedicated leadership position looking at the research agenda. And I set out the first 5 years of the research agenda through looking at kind of horizon scanning, looking at a survey of the financial kind of aspects in terms of what opportunities there would be for funding, different opportunities in terms of the research institute itself and its position within an academic institute. Historically, IPI had worked very much in isolation and not worked across the board at the Rochester Institute of Technology. And obviously tapping into the mindset and the knowledge of the staff of the team at IPI, both past and present. And here is our research mission as defined by myself during this process. And at first glance, it does seem fairly broad, but I think really the key points here is the words that are highlighted really speak to our priorities for the research agenda, but also the values of the team at IPI, which I think is really kind of important to kind of embed within our approach to research. There we go, that's a bit better. Okay, so IPI's research is always focused on the relationship between materials and their surrounding environment, with an emphasis on the end user and really thinking about practical outcomes and tangible guidelines and tools for the field itself. So that kind of impact at the end where the conservator is kind of at the fore of what we do is really kind of integral to our work. Over the past 2 decades, sustainable environmental management has really underpinned our research and has been part of the research program at IPI. And as we've just heard from Stefan, but also as we kind of know across the board, the majority of our museum and archive collections can safely be exposed to some degree of dynamic change in their immediate environment, which enables the broadening of recommended temperature and relative humidity whilst continuing to maintain preservation aims. However, there are many decades or maybe even centuries of conservation education that to some extent needs to be unpicked. And I say that as a trained conservator. So this is very much something that when I was training as a conservator, this idea of really kind of flatlining our environment was really part of our thinking around preventive conservation. So really, in terms of the way in which we want to approach our work at IPI moving forwards is really thinking about this accessible and impactful materials research and testing, developing user-friendly tools, and engagement and dialogue with relevant parties. Okay, so I think it's kind of important to speak to some of the work that went before at IPI. IPI was established in 1985 and was really one of the first places to develop preservation metrics and thinking about tools for managing collections environments and thinking around dose response functions really in relation to preservation guidelines. And there is a renewed interest in preservation metrics and how we can think about providing computational tools and modeling to help as a guidepost for collections managers managing their environment. So some of you may be familiar with the Preservation Index and Time-Weighted Preservation Index. And these were first developed in 1995 and designed to evaluate the preservation potential of different environments. The TWPI was developed to account for the dynamic nature of collection environments and to evaluate the cumulative impact of changing environments and chemical stability. As the name suggests, the Time-Weighted Preservation Index weights the time spent at temperature and RH according to their differences in reaction rates and the associated life expectancies. And this work was developed in conversation with colleagues at the Smithsonian Institute, so Mark McCormick-Goodhart and Marion Mecklenburg, who at the time were also looking at the impact of time out of cold storage for cellulose derivative decay. These preservation metrics were integrated into our software, so Climate Notebook, which was the desktop software, and latterly into eClimate Notebook. And then there were later additions, which was the % equilibrium moisture content and the % dimensional change metrics. And these were designed to estimate the quantity of water absorbed by hygroscopic objects based on bulk wood. And the % DC was calculated as a function of the tangential dimensional change of wooden objects and wooden materials. And these were really envisaged as early warning indicators for potential mechanical damage. Now, while PI and TWPI proved important tools for the field when assessing the likely impact of environmental set points on long-term preservation performance of collection spaces, the EMC and % DC metrics have seen far less significant usage. And their design was intended as an estimation of mechanical risk. And we know that mechanical risk is extremely complicated, which we will hear over the coming days. And I think their generalized approach is really being part of their limitation. So the inherent complexities underpinning these properties and mechanical properties really do highlight the need and opportunity for developing additional tools. And I think we'll hear a lot more about that tomorrow. And so with that in mind, I'm kind of looking forward to hearing about Dave Thickett's findings, where Dave Thickett on Thursday will compare a handful of metrics looking at mechanical change and comparing it to acoustic emission. All right, so I think I'm preaching to the converted here, but I do get the feeling that conservation fields really needs to readdress the balance between chemical, physical, and biological collection risks, and to study the synergies between them. My background is in conservation treatment, and it's always been in conservation research, and underpinning that research, it really requires an understanding of the chemical, but also a reflection on the mechanical properties of materials. It really does necessitate that. But across the field more broadly, the interplay between the chemistry of materials and the physical properties has been widely overlooked, certainly around education. It really isn't underpinning conservation training. So there remains a hesitance in the field to embrace a broader range of environmental conditions due to a fear to the mechanical properties, the mechanical changes to materials. And underpinning the adoption of sustainable environmental management is a need to demonstrate how cultural heritage materials respond to dynamic environmental changes, such as the rates of change, the magnitude of that change, and also the impact of cycling. And that in particular is for composite objects, complex 3D objects, and modern materials, which I feel that we have more work to be done in that area. So I guess with that in mind, the question is kind of where's IPI now? Well, our initial focus has been to secure funds for a mechanical analysis lab, which dovetails directly with our environmental control and incubation labs. And to date, we've purchased a dynamic mechanical analyzer to look at hydrothermal mechanical response, digital image correlation to look at in situ monitoring of strain responsive materials in situ, and a single-sided NMR for non-invasive time-resolved and depth-resolved relaxation monitoring. Our next steps will be to secure funding for mechanical test frame, but thankfully our position within the university means we do have colleagues and access to the mechanical engineering department. So this year, we've kickstarted the Dynamic Mechanical User Group for Cultural Heritage, and we've got colleagues here in the audience who are part of that group. And it's an informal group of peers, which is really interested in problem solving, method development, sharing of data. But we're looking to kind of develop this into a broader network. So if you are interested in participating, please do get in touch, and we'll next meet So underlying all of our current projects is an assessment of the static and dynamic relationship between equilibrium moisture content, water activity, relative humidity and temperature, and using DMA, DIC and magnetic resonance to interrogate how these factors influence mechanical properties of new and aged materials. We're looking to inform the wider implementation of sustainable environmental management strategies in collections through mechanical system operation, but also looking at passive control as well. And we aim to achieve this by bridging the gaps between model materials, but also in situ analysis of original materials in collections. So here on the screen is a title relating to a recent project that we've just had funded, where we're looking at two classes of polymer, namely cellulose acetate film and polyurethane foams, which are being synthesized in the laboratory with historically appropriate additive components. And here we're looking to address how different additive components and physical characteristics are influencing the equilibrium moisture content of plastics. We're looking at polymer class, polymer subclass, we're looking at surfactants, plasticizers, and the physical forms. So we're looking at film materials and three-dimensional network foams. And these are being studied in isolation, but also with painted surfaces. So we can look at this interplay in a composite material. This project is combining moisture content analysis and water activity measurements with static mode dynamic mechanical analysis to look at coefficients of thermal expansion and contraction and humidity expansion and contraction. And we'll also be looking at using the DIC later on in the project to assess object level response of materials in dynamic and fluctuating environments within our climate controlled walk-in chamber. We're looking at model samples and original materials from the British Film Institute, which will help us bridge this gap between the lab work and also kind of real world examples. And critically, we're looking to assess changes in EMC, but we're looking to see when we have materials in combination, when we have permanent strain and therefore potential damage to collection materials. But you'll hear a bit more about this project tomorrow when Jacek Olander will speak about it in greater depth. IPI has had a long-standing interest in two-dimensional printed materials, so it seems logical that we would look towards 3D printed materials as we move forward with the research agenda. And we've recently secured funding from NE8 to look at 3D printed materials in relation to their mechanical response. In this project, the mechanical properties of 3D materials will be studied across three major application uses. So we're going to look at three-dimensional printed materials for object fills in different dynamic environments. We'll be looking at creep behavior, as would be used as mechanical supports for objects on display, and then the damping properties for replacement parts in working objects. The focus will be on nylon, glass-filled nylon, and nylon that is not filled, and understanding how these materials respond differentially depending on the print orientation. We've chosen nylon because it's relatively inert and is used widely within the conservation profession, but also because we know that it has a high affinity to moisture absorption and therefore the properties are likely to change depending on their application and orientation of print. We're at the early stages, but we're starting to characterize the material, but we're aware that fused deposition modeling, because of the way in which the fibers are laid down, that there is an orientation aspect to the physical properties, whereas selected laser sintering, because it's produced with a powder bed fusion and it has a rastering of the laser, the orientation is less critical. So we're really interested in how we can guide preservation strategies and help support conservators make decisions about the best use for this technology with their particular application. We'll be working with the Strong Museum and we're working with the Cleveland Museum of Art, and this will essentially make sure that we are looking at kind of end user goals in terms of the application. These collaborators are already working with this technology, and we help to be able to guide that a little bit further. We've recently secured funding for a project looking at mold germination in dynamic environments during sustainable operation, but also during emergency response. And during this time, we'll be looking at dynamic environments, working in collaboration with Georgia Southern University, who will be doing the germination work. We don't intend to germinate in our labs, but we'll see. But we'll also be working with Colonial Williamsburg Foundation for on-site analysis. The lab experiments have been designed to establish the relationship between water activity at the surface of organic materials, fluctuating environments, moisture content, and rate of mold germination. And the on-site analysis will provide verification of how these materials actually respond over a long period of time seasonally with periodic analysis on site. We'll be looking to establish the relationship between water activity at the surface of organic materials and the surface relaxation properties using single-sided NMR, which is time resolved and depth resolved. So we'll be able to monitor over time during fluctuations. The information acquired relates directly to the proton density of the material. So we can monitor through the depth of a material how moisture is progressing. And this technique has been used in the food industry to look at mold germination in different types of food substrates. So we're hoping that we'll be able to take this instrument on site and conduct long-term analysis during fluctuations throughout the year. Okay, so our next steps for the research agenda will be to expand the scope of our energy and environment research. Whilst the energy and the environment is a very broad category, it really does underpin a lot of our research. We're looking to consolidate and grow our work around microclimates, especially kind of thinking around broader global climates and the need to think beyond North America. And looking at prediction modeling for energy optimization based on the interplay between the material and the environment. So we've just recently submitted a proposal, which we'll be working with one of the departments at RIT, our packaging science department. And we're looking at the use of phase change materials for thermal regulation and energy storage for objects in transit, but also objects on display and in storage. This work was spurred on by findings of a recent project looking at microclimates for paper-based objects during transit. And we were monitoring the interior conditions of crates and the exterior conditions of crates. We're working with 11 partner institutions across North America and Europe as objects were transiting globally. And here you can see on these graphs, this was something that a recurring theme that we found across the board pretty much, that during summer air transit, the interior of crates were actually seeing very high temperatures internally. And during winter truck transit, we were also seeing very low temperatures when we were transiting via truck. So these are just examples of what we were seeing, but we saw this recurring. And actually moisture incursion was not a huge issue with the crates that we were monitoring over time. We actually found that the RH was well controlled. There was a lot of buffering material. They were very well sealed. So it was actually the temperature changes that we saw the greatest fluctuation. Therefore, we're looking to review the use of phase change materials for different applications as a passive means of temperature control for regulation and energy storage. And we're going to be using the ASHRAE control specifications to really understand what the performance and the success of these materials might be when put under different stresses and different dynamic environments. We're going to look at cost, we're going to look at environmental sustainability, but also look at object risk as well, given that these materials do change phase. So it may well be that we can only apply them under certain circumstances. So where does that leave us now? Our next steps will be to introduce mechanical analysis testing services. This is a medium-term goal to dovetail with our chemical ISO testing that we already undertake as a lab. and to renew our pollutants research lab. Historically, IPI had pollutants research embedded within the program, but it's been about 15 years since that was active. So we're looking to reintroduce that in the interim. One last slide. So our aim is really to build on the Institute's long history of delivering translatable and accessible research to help guide preservation decisions and help people make decisions, not make decisions for them, but help conservators make decisions. And essentially, while we have a really good handle on the chemistry of objects, we're really looking to kind of be part of the readdressing of the balance, to look at some of these other priorities and other risks within collections with pollutants, microbiological attack, and also mechanical testing as well, and mechanical degradation. And with that, I'll leave it there. Thank you.
Thank you, Emma. Time for questions.
Oh, put my glasses on. Where am I looking?
Yeah, hi, thank you for the talk. So this is a very general question about humidity effects. So in these situations where temperature is also changing, is there a clear sense of what matters more? Is it the actual water content, so basically dew point, or RH that people should be tracking?
Yeah, so when you look at equilibrium moisture content curves, it's the RH that's having the greatest impact on that shift. As you look at how the temperature shifts over, if you look at moisture content, if you have it on you have your RH or your ERH, your equilibrium relative humidity, which is actually your water activity. It depends on what you put on your graph. But let's say you have EMC against RH, and then you plot the different temperature curves. Your RH is going to have the greatest impact. But the temperature is important in terms of how materials hold on to moisture. So as you go to colder temperatures, you see that there is a kind of a restraint on that moisture. So you can actually use that for some benefit in terms of buffering the conditions within things like crates and so forth. So we found that the greater issue that we had in terms of the crates that were in transit was that we were seeing large changes in temperature, but because there was a lot of buffering material inside the crate itself and a greater mass compared to the object, the moisture changes. We don't see a large drop in RH as we see an increase in temperature. We don't get this psychometric response. You actually see this hygrometric response from the buffering materials. So you can temper some of those temperature changes in terms of how moisture moves around by using buffering materials within crates. So we are looking at what the impact is in terms of temperature and RH and moisture content, but it's the moisture content that has the greatest impact in terms of what we're seeing in organic materials in terms of the strain response. But temperature does play a part in terms of how moisture is driven in and out of a material. But it's going to be the RH that's the biggest impact.
Okay.
Thank you.
Other questions?
Hi, thank you for your presentation.
Hey.
I'm not familiar with phase-changing materials. Could you provide an example, please?
Can I provide an example?
Of phase-changing materials.
An example?
Yes, of
Oh,
certain
sorry.
materials.
I was just yeah. So a water would be an example, as it's going through the melting temperature. So it's changing the phase of the material. So a lot of different materials, let me move to my little example here. So as you start to have material, it could be water. It's not going to be water, just to kind of say that now, that you get a change in terms of the phase, and therefore whether it it gives out energy or whether it takes in energy. So basically water would be an example of a material that is changing phase. If you went from a liquid to a solid or a liquid to a gas, it is changing phase. And during that process, there is an energy change. And so you can make use of this. So you may be familiar with pharmaceuticals that are transported through cold storage. If you receive pharmaceutical materials in the post, you'll quite often have these gelatinous materials that are being used to actually control and regulate the temperature. It's also being used within the building industry. So phase change materials are being impregnated into walls so that actually it can help regulate. So as the temperature increases, they will start to melt and they'll start to regulate the temperature. As the temperature decreases, they'll solidify again. So these are they're temporal changes, and they're not going to be applicable in all cases. So here we can kind of see that when the placement is going to be quite important in terms of the convection of the air, whether you're producing cool air or whether you're producing warm air. So it may well be that we find that when we look at phase change materials, as they're changing phase in warmer climates, we would need them to be above the object. Now that's going to increase the risk to the material, to the object itself. So doing a risk assessment to understand what the actual how we can contain these materials within different pockets, and they can be impregnated into materials, into the pores of materials, to see if we can contain them, because this is going to be quite important, the location, in terms of how it will regulate the heat and how it will store energy. So it's something that the team that we're working with on this from the packaging science department, they have a patent looking at phase change materials for the regulation of chocolate during transport. So their expertise, I think, will be really important for us to really understand how we might potentially utilize these materials that are melting and solidifying, and how we can use that in order to potentially regulate the temperature. And again, temperature is going to be important only for some materials. If we're passing through glass transition temperatures as materials are softening, if they're in transportation, if they're very brittle materials and there's potential of vibration. So the application of this is not a panacea. Temperature is not always going to be important, but certainly when we were seeing these very large spikes in temperature and drops in temperature, we were thinking, is there a better way in which we might be able to regulate for shorter periods of time during transit? So watch this space. This work hasn't been done yet. But we'll hopefully be reporting out in a couple of years, and we'll see how it works.
Emma, thank you very much.
Thank you.
Thank you very much.